So for the past few years, you guys have been learning about inverse operations, which we use to solve for an unknown variable and to balance equations. They're also known as opposite operations. So we know that the opposite of addition is subtraction, and the opposite of subtraction is addition. So you'll remember that if we had x plus 3 equals 9, if we wanted to isolate x, we would subtract 3 because subtraction is the opposite of addition. This would essentially cancel everything out, leaving us with x equals 6. We could also think about it in terms of balancing the equation. What plus 3 equals 9? Well, 6 plus 3 equals 9, therefore x must equal 6. We can also think about this in terms of subtraction. So if we had x minus 3 equals 9, and we would want to isolate x again, so we would add 3 because addition is the opposite of subtraction, and whatever we do to one side, we do to the other. This gives us x equals 12. Likewise, if we wanted to think about this in terms of balancing the equation, what minus 3 equals 9? Well, 12 take away 3 equals 9, right? So we get the same answer no matter which way we think about it. So we know that addition and subtraction are the opposite of one another, and they help us solve equations. Multiplication and division are the other opposites that we've learned so far. So if we had something like 3 times x equals 9, and we wanted to isolate x, we would divide by 3, because division is the opposite, but whatever we do to one side, we do to the other, leaving us with x equals 3. Or, if we wanted to think about it in terms of balancing, 3 times what equals 9? Well, I know that 3 times 3 equals 9. So again, it doesn't matter which way we think about it. As long as we're balancing the equation or solving for the unknown, we get to the same answer. We're now going to add a new layer of inverse operations, and that is squares and square roots. So whenever we have an exponent, that means that we don't have a single x. Our goal is to always isolate the variable or balance the equation, right? For all of these problems we've done so far, we've always solved for x equals something, but it's one x, not 2, not 3, not 4. So when we have an exponent, we're going to use square roots and roots in general to get the x by itself. So let's go through an example. Let's say we had x squared equals 9. Well, I want to get x by itself. I know that the opposite of a square is a square root. So I'm going to square x squared. But whatever I do to one side, I have to do to the other, just like the other operation. So we're going to square everything. When we do this, it's going to give us a single x. And that is because a square root looks for groups of 2. There's always an imaginary 2 right here. You just don't see it. But it's looking for groups of 2. And when we have a group of 2, one can stay in and one can escape. Same if we had y squared. That would technically be y times y. So one can stay in and one can escape, right? Squares are just a way of getting the variable by itself if it has an exponent. So we're thinking about what times what would give us x squared. Well, x times x will give us x squared. What times what will give us 9? Well, we want to think of same. I know that 3 times 3 will give us 9. So if we took the square root of the two x's, we'd be left with x. If we took the square root of the two 3's, what do you think we'd be left with? Hopefully you thought to yourself, just 3. Again, when you take a square root and you have a double, you can think of, I always say, one dies and one escapes. But really you're just pulling one out of the group. Let's try another example. If we had, let's say it's y squared equals 16. Well, I want to solve for y, a single y. So I'm going to square root the left side, but whatever I do to one side, I do to the other. Now we're going to think of doubles. I know that y times y equals y squared. I know that 4 times 4 equals 16. So if I take the square root of these y's, it leaves me with y. And the square root of these two 4's leaves me with just 4. You might have noticed by now that every time there's a perfect square, such as 1, 4, 9, 16, 25, 36, 49, nothing in 50, 64, 81, and 100, right? These are perfect squares, meaning 1 times 1 equals 1. 2 times 2 equals 4. 3 times 3 equals 9. 4 times 4 equals 16. 5 times 5. 6 times 6. So on and so forth. These are numbers that are made by multiplying the same number by itself. So if you're given one of these numbers, if you take the square root of them, you're always going to get a perfect answer, or a rounded number. Square root of 4 will just be 2. The square root of 9 will just be 3. The square root of 16 will just be 4. We're going to talk about this a lot more next quarter, but for now we just need to know that when we're given a perfect square like these numbers and you take their square root, you're thinking of what number multiplied by itself gives us this number, and then that'll be your singular answer.